Hello, I'm Miguel Zumalacarregui, and today I'm going to tell you about novel tests of gravitational wave propagation and their potential to test dark energy. First, let's start by remembering that tests of gravity and dark energy are very important, as gravity is linked to a wide number of unsolved problems in physics. Dark energy is also the dominant cosmological component, and we want to test that. And also, especially since increasingly precise observations appear to cast doubt on the possibility that a cosmological constant, the simplest dark energy theory, is the right description. For these reasons, we want to test gravity and dark energy with as many observations as possible. And in this sense, gravitational waves are a very unique and powerful messenger. They are the only messenger that gives us a signal that we can predict ab initio from theory using a variety of methods. Here you're seeing a numerical relativity simulation of two black holes. And as they emit gravitational radiation, they come closer, increasing the frequency and the amplitude of the wave in a way that Einstein's theory allows us to predict very precisely. This leads to a rich structure on gravitational wave signals that allow us to infer the properties of the source, such as masses, spin, and orbit, and also encode directly the dynamics of the gravitational sector. And we can use this to test gravitational waves at various stages, not only emission, but also propagation and even detection. In terms of tests of gravity, one of the more natural things we can do is to test how gravitational waves are emitted. And this is a way to probe the strong field dynamical regime. This gives us often the best constraints on theories that modify general relativity in the high curvature regime. For example, Gauss-Bonnet gravity. But these theories are typically unrelated to cosmological and dark energy models. It's very difficult to gain insights into cosmological theories from this kind of tests. To this, we turn to propagation of gravitational waves. And most of the effort here has focused on a homogeneous cosmological background, where we know that gravitational waves can teach us about cosmological gravity and allows us to constrain dark energy theories beyond GR. And because the cosmological background is very simple, there are basically 4 different ways in which we can modify the propagation of gravitational waves. Here I'm showing the equation very schematically, and there are basically 4 terms that we can parameterize and constrain. The first one is the speed. So it's a 2-derivative correction to the 2-derivative term. And this is very strongly constrained from a single multi-messenger observations in which gamma rays were observed just 1.7 seconds after the coalescence of a neutron star merger. This is extremely tight constrained and is very powerful on theories that have derivative interactions. For example, a derivative coupling between the Ricci scalar and scalar field. These theories are very strongly constrained. They're pretty much useless for dark energy, but most theories that we deal with are not, do not involve this type of interactions and are therefore unconstrained. A much more universal deviation from GR is a damping term. So this affects the relative amplitude of gravitational waves, for example, relative to standard sirens. However, the constraints are much weaker. Here I'm showing the limits from the latest results of the LIGO-Virgo-Cagra analysis, where the constraints on this parameter, Cm, assuming a certain parameterization for the damping, are give order 1 constraints. And this is using over 200 gravitational wave events correlated with galaxies. Now, that's the disadvantage. The good thing is that this constrains any non-minimal theory of gravity. So in this case, we can couple the Ricci scalar to the field, not necessarily to its derivatives. And I would say there's a very extreme variant of this where gravitons or gravitational waves, classical gravitational waves, can decay into scalar modes. But this only happens in Biot-Hordensky theories, like it's very, very extreme deviations. Now, the next thing we can have is a mass term or interactions with other fields. A mass term leads to dispersion, so it causes the low frequency components of a wave packet to propagate slightly slower and arrive later. This distorts the signal and allows people to put constraints. A bit more interesting is when there are interactions with additional degrees of freedom. For example, in bigravity, we can have oscillations between different gravitational wave states. This is analogous to neutrino oscillations, where the propagation and the interaction states are defined differently and leads to very rich phenomenology. However, this propagation in Friedman-Robertson-Walker is quite limited because we have basically two effects, the speed and the damping, that do not distort the waveform. And therefore, observing them relies on multi-messenger observations, either with multi-messenger observations of the same source or cross-correlating with other sources, or using properties of the population to make up the fact that we cannot access the redshift. The other two classes of modifications, dispersion and interactions, do lead to waveform distortions, but they do not happen in simple theories like scalar tensor theories. They need a massive graviton or several. And the reason for that is that the Friedman-Robertson-Walker is too symmetric. So we need to break this assumption to be able to constrain, to unleash new effects. And this leads us to the idea of gravitational wave lensing. Now, gravitational wave lensing is something we expect. Gravitational waves travel through the universe. They will encounter gravitational fields. But there are some differences. So they're very coherent, they're understood. And now I'm showing in this movie how when they encounter a galaxy, they will undergo focusing by the gravitational field of the galaxy, and this will lead to a chromatic, frequency-independent amplification of the signal. But there are other effects. In the case of gravitational waves for ground detectors, if we zoom in, smaller objects whose gravitational radius is comparable to the frequency will lead to distortions of the wavefront. And these are analogous to diffraction, which is a chromatic or frequency-dependent effect, and will lead to a distortion of the signal that we can observe and use to identify lens gravitational waves. In general relativity, diffraction is the main effect we have, at least in weak fields. And I will not go into the details, but I just want to flash some results of a recently reported event that is consistent with gravitational wave diffraction. And in our analysis and others, this allows us to place this event potentially even beyond the detector horizon as a diffracted and also gravitational magnified black hole merger. There's additional wave optical effects. So diffraction is what happens for GR in the weak field limit, but we can also have dispersion or frequency-dependent propagation effect, like a rainbow forming in a prism, and even birefringence, that is polarization-dependent propagation. This can happen in GR under strong gravitational fields, so very near an intermediate mass black hole. And it can also happen in theories beyond Einstein gravity, which will be the subject of the remainder of my talk. So the idea here is that when we introduce an inhomogeneity in the space-time, imagine a gravitational lens as shown here, there are new interactions. This inhomogeneity sources a non-trivial configuration of the non-GR field, say a scalar field, and this leads to new interactions with the standard gravitational wave polarizations. These couplings are absent in GR and lead to a plethora of new effects. And the idea is what I mentioned before in the case of bigravity, is that in the presence of these inhomogeneities, the states that propagate are different. They propagate with the well-defined properties are a different combination of the what we nominally call the metric or the additional degrees of freedom. To see how it works, let's look at the structure of the equation, which I'm writing here on top. This mimics very closely what I wrote before in the case of Riemann, Robertson, Walker. And the main difference is that we're now writing the propagating degrees of freedom as a vector with 3 or more components after fixing the gauge. The first term is modifications or interactions in the kinetic term, which is analogous to the speed, and this changes the phase. The second class of terms are frictions that typically encode the amplitude evolution. And this is related to the damping. And finally, we have mass terms, which are related to the phase of the gravitational waves and the phase in a frequency-dependent way, which is analogous to dispersion. Now let's look at the propagation eigenstate in a theory in which we modify the interactions between fields at the kinetic level. And let's look at a scalar tensor theory where I'm writing this kinetic matrix in this way. It's a matrix made of second derivative interactions. So there are diagonal terms. Each of them is characterized by a certain speed. And I'm including a non-diagonal derivative interaction between one of the gravitational wave polarizations and the scalar field. This is, by the way, what describes propagation in the high frequency limit. We can derive this in a shortwave or WKB expansion. So this is a matrix equation that we can diagonalize. And the first thing we find is, you can see this from here, there's a pure metric eigenstate, which in this, the way I've written this, is just the h cross that travels at the speed at which gravitational waves travel on the cosmological spacetime, call it ch. And then there's 2 states that mix the 2 other components. And one of these, if this M phi matrix mixing term is small, one of these states will be a Moseley metric. So it will be the plus polarization plus a small correction that mixes it with the scalar field. And very importantly, this mixing will cause a slight difference in the speed of this Moseley metric polarization. And then finally, there will be a Moseley scalar mode that already travels in general at a different speed, but this speed will be nevertheless a little bit modified. This is very rich. This leads to birefringence, similar to how shooting light through a complex crystal can split it into the 2 polarizations. And these polarizations, if they're separated by time delay shorter than the signal, will lead to a distortion of the waveform, as shown here for a 50 millisecond delay. This allows us to not rely on multi-messenger or electromagnetic observations, but just use individual black holes to search for this effect. And it's something that we did. So I'm showing on the right the constraints on selected binary black hole events. And on the left, I'm showing the limits that you can place, given there's no detection, on an example Hordensky theory that has a derivative interaction as well as a non-derivative interaction. And these limits are comparable, not as stringent, but comparable to what you would get from the speed of gravitational waves on a cosmological background. Now note that one of these events seems to prefer a slight delay of about 10 milliseconds. So we don't believe this is a real deviation from general relativity. This is probably better accounted by noise in the detector. The event itself is fits a lot of non-standard explanations, but for the sake of argument, I'm showing here what you would get if you assume that this is binary was generated close of nuclear, the supermassive black hole of AGN, which is something that has been proposed in the literature, in which case you could increase, but you assume there's no deviation, you could increase these constraints to the red region here. And if you assume that this 10 millisecond is delay is for real, and that that it's also an AGN event near a supermassive black hole, we can exclude the region below, which is what would produce delays smaller than 10 milliseconds. And this includes general relativity, which would be the limit of infinite coupling suppression and zero coupling, zero conformal coupling. So this is showing how these theories can be tested. Something very exciting that we are recently uncovering is that if we look at the mass terms, they lead to dispersion, so frequency-dependent effects that modify the waveform, as I'm showing here on the right. And what's most interesting is that these effects, which are absent in GR in vacuum, require no derivatives. So therefore, they will be universal in non-minimal theories of gravity, where there is a non-minimal coupling between the metric and any additional field. I will not go into the details. I refer you to the talk by Nicola Menadeo on this subject, who is the researcher who has carried out this study. Now, this case, I'm showing relatively small dispersive modifications of the signal, but we have also more recently studied this in other theories and realized that there can be cases where dispersion can be extreme. So normally we assume that the frequency squared that comes from these derivative terms is much larger than the mass term. However, if this is flipped, if the mass terms are bigger than the kinetic energy of the gravitational waves, in some region, the gravitational waves will be blocked or reflected in a phenomenon analogous to plasma blocking of radio waves by the Earth's atmosphere. Now, if we take this, we can study this for symmetron gravity. Here I'm showing potential limits of the symmetron parameters if we assume, if we take the region where the Earth or even the Moon for a decifers detector could block gravitational waves. Of course, this is playing a dangerous game because we are working beyond in a region where our assumptions are not, shortwave expansion is not correct. So a framework needs to be developed, but I believe that this is very promising as a test of dark energy theories. Now I leave you with my conclusions. Gravitational waves are a unique messenger and offer rich tests of GR through the propagation of gravitational waves. But tests on a Friedmann-Robertson-Walker universe are very limited because there are just a number of effects we can have, and then we're limited by counterparts or assumptions in the population or specific theories with massive gravitons. So gravitational wave lensing, although very challenging from a theoretical computational point of view, is the natural extension of this program with rich effects like birefringence and dispersion, perhaps even leading to dramatic departures like gravitational wave blocking. There's a lot of work to do, including developing a formalism, unveiling new effects, extending these to other theories and deriving constraints. And I'll be very happy to discuss more with you in the asynchronous sessions. Thank you very much.